Welcome, everybody, once again to the Amateur Astronomers Association of Princeton, our first meeting of the new year. I know everybody has had quite an experience getting through December with our big storms, and here's another one to start the new year. And we like to think back at the good old days when temperatures were cold in Princeton. This would have been, what, 3 feet of snow by now at least. So a bit irregular and a bit rugged out there tonight, and hence we're all meeting on Zoom. I think you can see it's for the betterment of everybody that we're not trying to hoof it from the parking garage. Although we, until the very last minute, wanted to, but it turns out the governor himself declared an emergency for the state. So Princeton was happy that we were not going to be traipsing mud into Peyton Hall. In fact, Peyton is closed as of 5 p.m., I understand. So we have a good meeting planned for you all tonight. I know, looking through the group here on the Zoom, a number of new members, as well as some of our longstanding and experienced and knowledgeable members on board. So I hope you'll find it a good experience tonight. The way we will run this, as we typically do, is just a couple of quick announcements, not really announcements, a couple of things to pique your interest, I think, and then I'll turn it over to Victor, who will introduce our speaker. And we're very grateful to have a really excellent speaker tonight, really looking forward to the talk. We will allow her to go as long as she likes, but I mean, typically an hour, including questions, or a little over is fine. And then we'll take an intermission. And then we'll come back and talk about what's happening in the AAAP in terms of members' contributions in astronomy. And as nobody else has stood up to do an Unjournal Club, then I'm afraid you've got me on the agenda. So I'm going to talk about something that I've been thinking about. I'm calling it hidden hydrogen. And then we'll talk about some of the outreach activities and maybe talk about what's happening in the observatory. And we'll have time at the end. Anyone on the call here, member or otherwise, that has questions or comments or ideas, you'll have an opportunity to speak up. And I encourage you to do this so that we can all get to know one another. By the way, my name is Rex Parker, for those of you who don't know me, and I am the director of AAAP this year. So good to see you all. A great way to get ourselves thinking about astronomy is to consider what's really up in the sky. And at this time of year, we're kind of in a transition as the excellent constellations of winter really approach their best position at the bottom part of the screen, Taurus, and you can barely see Orion on the lower left. But what I want to call your attention to is something I find really intriguing. Using the star chart from the Sky 10, I brought up a number of the optional databases that can display some of the emission nebula classes that we don't commonly see and talk about. And all these red circles following along the disk of the arm of the Milky Way from lower left to upper right, all these are representing a class of nebula, most of them known as H2 regions, hydrogen 2 regions. They are classes of emission nebula, which are vast clouds of interstellar gas of mainly hydrogen, which is emitting light in the reddish wavelength according to the spectrum of ionized hydrogen. So H2, because the 2 form of hydrogen astronomers consider is the ionized form, ionized by the light of stars illuminating them. And I got very curious about these because these are not things that we typically look at with a telescope. They're challenging objects, but using my rig here at home and a special filter that we can talk about after the break, perhaps, using the filter that can bring in the wavelengths of hydrogen alpha as well as oxygen 3 and sulfur 2, I was able to image one of these types of objects. And this is an H2 region in Cassiopeia. It has an IC nomenclature. That's a certain catalog that classifies nebula. This image is about 1 degree of angular diameter, 58 by 39 arc minutes. So you can see the size of it, about the size of 2 full moon diameters. And this is an example of all those red dots on the star chart I was just talking about, what it would really look like if you could see them in all their glory, which I found quite astonishing. I wanted to learn a little bit more about these. And so after the break, I'm going to get into this a little bit more, and maybe you'll find it interesting as well. And then just one last thing, just to get everybody's brain moving. Here it is, big storm going outside, and we want to concentrate on astronomy. So I whipped up a little astro quiz. And what I'm going to do is flash this to you, and maybe just with pen and pencil back at home there, just jot down your answers to these, and we'll see how well you did after the break. Now, these are easy questions. These are Astro 101 questions, but I wonder how many of you are actually going to remember all of them. So what are the 6 most abundant elements in our solar system? Which is larger, a light year or a parsec, and how many light years or parsecs in a light year? What is the approximate diameter of our galaxy? How long does it take for our solar system to make a revolution around the galaxy? Did you realize that our solar system makes revolutions around the galaxy? And then finally, this is an easy one. This is a giveaway. How many times brighter is a 1st magnitude star compared to a 6th magnitude star? I know some of you have got these right off the top of your head. No going to AI, no asking Siri, all right? This is on the top of your head. Stare at those for a minute and then we'll move on. In fact, at this point, I am going to ask Victor to get ready to come up here on the Zoom and begin to introduce our speaker for the evening, which will, I'm sure, bring us much more deeply into the sky. So here we go. Victor, over to you. I'll stop sharing my screen.
Okay, thanks, Brett. Well, it's a pleasure to introduce the guest speaker. And I wanted to thank you to also Michael DeMario, who suggested the guest speaker for tonight. Dr. Leah Medeiros. The Event Horizon Telescope, which we've all heard about, is a very long baseline interferometer incorporating several radio telescopes spread all over the world. The AHT performed its first observations in early 2017, and the first image of a black hole at the center of the nearby galaxy M87 were published on April 10th, 2020. The sparse interferometric coverage of the AHT makes reconstruction of black hole images challenging. PRIMO is a new algorithm for image reconstruction that builds principal components from high-fidelity general relativistic magnetohydrodynamic simulations of low-luminosity accretion flows. This allows researchers to reconstruct images that are both consistent with the interferometric data and that live in the space spanned by the simulations. We'll hear a lot of that in her talk. A few words about our guest speaker. Leah Medeiros grew up in Brazil and spent a few years in Cambridge, England. She completed her undergraduate education in physics and astrophysics from the University of California, Berkeley, and her master's and PhD in physics at University of California, Santa Barbara. She's currently an Einstein Fellow in the NASA Hubble Fellowship Program at Princeton University. She was a member of the Institute for Advanced Study from 2019 to 2023 and an NSF Astronomy and Astrophysics postdoc fellow from 2019 to 2022. After completing her classes in Santa Barbara, Dr. Medeiros took advantage of the flexibility allowed by an NSF graduate research fellowship and spent 3 years at the Steward Observatory at the University of Arizona and 1 year at the Black Hole Initiative at Harvard. She's lectured to academic and public audiences in both Portuguese and English. She loves horseback riding, practicing aerial silks. You'll have to describe what that is, I'm curious. Salsa dancing and almost any type of art, especially ceramics and drawing. So thank you, Dr. Medeiros, for being with us tonight.
Now it's moving.
Select the video, yes. Is this good?
Yes.
Okay, fantastic. And sorry about that, that did not work the first time, but glad we got it working now. So as I was saying, the thing that you are now looking at, but you were not looking at before, is the result of a simulation. And the way that we make these simulations is that we effectively just give the computer, specifically a supercomputer, a bunch of physics equations. And then the computer uses those equations to generate images like the one you see here. In particular, the physics that is relevant here is that we actually have matter that is swirling around the black hole and eventually falling into the black hole. That matter actually gets incredibly hot. So hot, in fact, that it becomes a plasma, which means that we have a bunch of charged particles moving around. Now, the black hole also has a magnetic field. And so we have a bunch of charged particles that are moving through a magnetic field. And according to the laws of electromagnetism, that's going to have some interesting effects. And what you see here, the fact that this is variable, right, the image is changing, really comes from the interaction between the plasma or these charged particles with the magnetic field. It acts almost like turbulence, like what you would see if you were to, stir your coffee or something like that. But what's giving us the viscosity, instead of it being the interaction between particles in a fluid, it is the interaction between the charged particles and the magnetic field. So we call it magnetohydrodynamic turbulence. There will not be a quiz. You do not need to remember that word. Just in case you were worried. What is particularly interesting is that without the turbulence, the matter actually wouldn't fall into the black hole. So it's actually really important, because that's how we can lose some angular momentum for the matter to actually be able to spiral into the black hole and not just be in a stable orbit. What you're looking at here is actually not the matter itself, but rather the light that matter should be emitting according to the laws of physics. And in particular, you're looking at light that has a wavelength that is in the radio spectrum. So I'm assuming most of you guys work in optical. Everything I'm going to be talking about today is all going to be in the radio. And this is actually a free color image. So green is equivalent to 0.8 millimeters, which is 345 gigahertz. Blue is 1.3 millimeters, which is 230 gigahertz. And red is 3 millimeters, which is about 86 gigahertz. The Event Horizon Telescope, or EHT, so far has only published images at 230 gigahertz or 1.3 millimeters. But as I will kind of tell you later on, we are working on being able to observe these other wavelengths as well. Okay. So the way that I wanted to get us started here is to first talk about what is the image of the black hole and what we can actually learn from that. Then we're going to talk about the instrument itself, and then finally the actual algorithm that I have kind of introduced on my title. So the very first time that somebody thought about what you might see if you were to look at a black hole was in the 70s. And the image that you see here is actually from one of those original papers. It's from one of the very first papers, actually. And in that paper, they calculated what you would see if somebody was shining a infinitely large flashlight on a black hole, and if you were to look at that black hole. A couple things I want to point out here. The top panel and the bottom panel are at the same scale. The top panel is showing you the size of the event horizon of this black hole by this filled black circle here. The bottom panel is the image that you would see that this paper calculates. And you see that there is a dark filled region, and then it's encircled by a bright ring of light. Again, these are at the same scale, meaning that this dark region is significantly larger than the actual size of the event horizon. We tend to refer to this filled dark region as the black hole shadow. However, you should be a little bit careful with that, because some of your intuition about that word might not be quite so simple when you think about what it does when you look at a black hole. And so Lee Sandberg, who I believe is on this call, is a colleague of mine at the IAS, and we work together to come up with what I think are really cute and really useful diagrams that I'm going to show you here. So we're going to start with talking about the shadow of a soccer ball. I'm from Brazil, so this is obviously a football, but I will concede and call it a soccer ball for now. If you had this helpful little guy here, shining an infinitely large flashlight on a soccer ball, the diameter of the light beams that would be blocked or absorbed by the soccer ball is going to be equal to the diameter of the soccer ball, because of course all of these rays of light are going to move in a straight line. However, when we are dealing with a black hole, it's a lot more complicated. And of course, our helpful little guy here is now in grave danger, and we are all very concerned. The difference, of course, is the fact that now light is not just moving in a straight line. The reason for that is that the black hole is so powerful gravitationally that it will really significantly affect the geometry of space-time itself. So according to Einstein's theory of gravity, gravity itself is a curvature of space-time. And everything that is moving under the force of gravity is actually just trying its very best to move in a straight line, but it's not able to move in a straight line because it must move through a space that has an inherent curvature, the same way that if you were to put an ant on the surface of a sphere, it's going to try really hard to move in a straight line, but it won't be able to because it's on the surface of a sphere, so it's going to have a curved path. Given all of that, the light here is trying really hard to go in a straight line, but it just cannot do so due to the curvature of space-time caused by the presence of this black hole. And so even though the actual size of the event horizon is the same in this diagram as the size of the soccer ball, the size of the shadow is going to be much greater, actually about 2.5 times greater. And the reason for that is that we define what the black hole shadow is as the critical photon between photons that fall in and photons that escape. And so by that definition, the size of the black hole shadow is going to be given by the size of all of these photons here, or all of these rays of light that are going to fall into the black hole. And so that's going to be 24 inches as opposed to about 9 inches, right? So again, about 2.5 times bigger. Okay, so I'm bringing you back to that simulation that I had on my title slide, because I want to kind of explain why the word shadow is a little bit tricky. Given the fact that it's called a shadow, most of you are probably assuming that it's this dark spot at the center here, right? It's actually not. It's actually much bigger than that. And it's coincident, the boundary of the shadow is coincident with this very thin, bright white ring. The fact that it is thin is important. The fact that it's white is also important because it's showing you that it is achromatic, because it's a gravity feature and not an astrophysics feature. And also it's completely constant while everything else varies around it, again, because it's a gravitational feature. I'm going to highlight this circle with a dashed black circle now, just to make sure everyone can see in case you couldn't see my cursor. And the point here is that given the definition that I've used for what the black hole shadow is, this is the boundary of that feature. And now that I've defined what the black hole shadow is in a way that depends only on the black hole itself, we now need to ask ourselves, how is the image that we actually see related to or not related to this gravitational feature that we've defined? Okay, so this is another result from a simulation. You'll notice that it looks quite different. These yellow features here and down here, these are the jets of this black hole. And this kind of orangey feature here, this is the disk of plasma that is swirling around the black hole and falling into the black hole, but also a little bit does get ejected into the jet. A few things you'll notice is that you cannot see the black hole shadow. The reason for that is that we are looking at right now light that has a wavelength of 1 centimeter. So it's actually quite long. It is still obviously in the radio spectrum, but it's quite long compared to the 1.3 millimeters that we actually observe at. What you're seeing here is the reason why we observe at 1.3 millimeters. If we were to observe at 1 centimeter, we would get a lot of really beautiful pictures of the disk and the jet, but we obviously would not be able to learn much about the black hole itself because we would not be able to see the black hole shadow itself. So it wouldn't really be an image of the black hole, it'd really be an image of the disk. And so this is also an animation. I'm going to play it soon, and we're going to go from 1 centimeter all the way down to 1.3 millimeters. As I shorten the wavelength, you will see that the disk will become optically thin, or it will become transparent. We will actually be able to see through the disk all the way down to the black hole shadow. One of the ways that you can think about this is that it's almost like we're taking an X-ray of the black hole. We are choosing a wavelength of light that we know can pass through the disk, just like X-rays we know can pass through human skin and human flesh, so that we can get an image of the part that we actually want, which is the shadow. And again, in the analogy with X-rays, obviously you see your bones. Okay, so I'm going to go ahead and play this. You'll see that the disk becomes optically thin. It's completely transparent now. We are at 1.3 millimeters. I'm going to zoom in a little bit so you can see more of the details, and then it's actually going to play as a function of time. Again, there is a lot of variability. That is a really important aspect of this, and that does come from the turbulence. But you can see here that we see the boundary of the black hole shadow is this ring that you can only really see part of it here due to the inclination of the black hole relative to the observer in this particular simulation. Okay, so now that we've learned a little bit about what the image actually is showing us, I want to motivate a little bit as to why this image is actually so useful and so important to us in the first place. So for me personally, I'm really interested in gravity and black holes themselves. And I am really interested in using black holes in space to learn more about gravity itself, and specifically to test Einstein's theory of gravity. So I like to say that I use black holes in space as laboratories. The image that you're seeing here is an artist's depiction. And again, I have Lee Sandberg to thank for this. I worked with him to write an article for the IAS Institute letter that explained how we use the black hole image to test gravity and how we use it as a laboratory. And so he contacted this amazing artist to draw her vision of what a black hole lab would look like. My favorite part actually is that a lot of these scientists are subtly women, that when you first look at it, it's not, in your face, but when you actually look at each of them, most of them are actually women, which is very, very cool to me. And I just think it's beautiful. So anyway, so this is our black hole lab. What are we actually doing here? What is the actual experiment? Well, when we talk about testing gravity, what's really important to keep in mind is that according to Einstein's theory, it's not just that this theory predicts black holes, but actually it predicts a really specific black hole. What I mean by that is that the black hole in space needs to have a very specific geometry. And if it has a different geometry, then something really, really fundamental is wrong about how we understand black holes and gravity itself. And since the amount by which light is curved depends on the specific details of the geometry of the black hole, if we measure the size of that ring of emission or the size of the black hole shadow, we can use that to test whether or not these black holes in space are consistent with Einstein's prediction or not. And so this is kind of the motivation why it's so important to me to make these images, and also what we actually do with the images once we have them. Okay, so now that we've outlined what the image is and why the image is important, we also need to discuss how we're actually going to go about making the image, which in many ways is the hardest part. So if you do a very simple calculation of, given the size of the black hole shadow, given the distance to the black hole, given the wavelength that we're observing at, what would be the size of the telescope that we would need? Well, it turns out that it's about the size of the Earth. And that's a little outside of our budget. Also, people would notice. It would be very dark on half the world. People would be upset. And so obviously we can't do that. But we do the next best thing, which is very long baseline interferometry. Now, this is the part of the talk that is getting a little bit more technical. And the reason that I decided to include it is that for those of you that are interested, I really did want to give you the opportunity to fully understand the ins and outs of how we actually collect our data and then how we use the data to make an image. And I think that that'll be helpful in really understanding what the algorithm I developed does. If this is not really your cup of tea, don't worry, it's not going to be the rest of the talk. So you can just kind of zone out for a little bit and I'll call you back in a bit. Okay, so with all of those caveats out of the way, the picture that we have here is that we have a black hole that is emitting radio waves, and those radio waves are traveling towards the Earth. In this example, I have 2 telescopes at different locations on Earth, and each radio wave will arrive at one telescope at a slightly different time compared to the other telescope. And we actually have incredibly precise clocks at each of our telescopes. They're actually atomic clocks, they're hydrogen masers, and they're a really important part of our instrument because it's incredibly important or really crucial for us to measure really precisely the arrival time of each of the radio wavelengths at each of our telescopes. And then we record all of this data to a hard drive at each of the telescopes. We collect an insane amount of data. The reason for that is that instead of just having a pixel that just has a number associated with it, which is just the total number of photons it's collected, instead of that, it's almost like we're, taking an entire profile of each photon we collect, right? We're asking exactly what time each photon arrived, what the wavelength was, what the amplitude, the phase, everything. And so we collect a lot more data for each photon that we actually receive. And then the only way to actually transport all of this data, because in 2017, for example, we collected about 7 petabytes of data. The only way to transport it is to literally put all of the hard drives, which, by the way, there are many hard drives, to put them all into a wooden crate, and then to put that crate in an airplane and to fly it, because otherwise it would just be impossible for us to transfer all that data. And so all of the telescopes send their data by plane to the same location where we have a supercomputer that's been specifically designed to be able to solve the really complex mathematical problem of using all of the information that we collect from all of our photons to figure out exactly where in the image each photon was emitted. So as an analogy here, what we're doing is kind of similar to the way GPS works on your phone. So the way that GPS works is that your phone communicates or sends radio waves to a bunch of telescopes that are surrounding the Earth, and it measures the time delay between each signal moving from the phone to each of the telescopes. And so each signal will arrive at satellite, will arrive at each satellite at a different time. And they use these different time delays to triangulate specifically where the phone is, really precisely. And so we're doing something similar here. We are using the time delays to determine precisely where in the image each photon really originated. And that gives us an effective resolution that's much higher than what we would get from any individual telescope. Okay, we're still continuing in the technical stuff, but don't worry, there's not that much more left. Okay, so what we do with these telescopes, I've kind of give you a little bit of an intro so far, but our data also looks very different, right? So the data that we get out of this supercomputer, it's not 7 petabytes, it's very small actually, but it's in a weird mathematical space. And so for those of you who have learned about Fourier space, I will just say that this is in Fourier space, but if you are not familiar, the way that you can think about this is that there is a mathematical equation that can take your information from the image space to a different space, and then the same math equation can take you back again with obviously it's the inverse of that math equation, but effectively the same thing. And you can go back and forth as much as you want. If you're not interested in this stuff, that's really all you need to know for the rest of the talk, is just that there's an equation and you can think about it as like a black box, image goes in, data comes out the other end, and that's fine. If you want to know a little bit more about what this is, what the Fourier transform actually does is that it converts your information into a different space, where in that space, it's like you are approximating, let's say, a curve with an infinite number of sines and cosines. And so the idea here is you can add and subtract sines of different amplitude, specifically like the sine curve, right, of different amplitude and different phase, to approximate any curve that you might want to approximate. When I move my information into Fourier space, instead of actually having the curve, I have the information about these amplitudes and phases that I would need to be able to approximate it with these sines and cosines. Another important detail is that our data is actually complex. So they're literal complex numbers. We have amplitude and phase, because again, we do need both an amplitude and phase to be able to use the sine waves to approximate the original image. Okay, so all of that explanation is actually in 2 dimensions. So instead of a curve, we have an image, but it all works out in 2 dimensions the same way. And each pair of telescopes on Earth can collect information about one specific location in Fourier space, or in other words, it collects information about one specific length of sine wave. And in particular, the distance between the 2 telescopes is going to determine the distance from the center of Fourier space where we can observe. And information that is in the center of Fourier space is telling you about low spatial frequency, which just means it's going to tell you information about the largest structures in your image. And as you get farther and farther from the center of Fourier space, you're going to learn about smaller and smaller structure in your image. What this means in practice is that if you put your telescopes farther apart on Earth, you will observe a region of Fourier space that is farther from the center, which will mean that you will have information about small scale structures, which gives you a higher resolution image. So by putting our telescopes really far apart, we can get a higher resolution. You'll see that the distance L here determines this location, but it's also divided by lambda. Lambda here is the wavelength at which we are observing, not the wavelength in terms of spatial frequency and Fourier transform, but the actual wavelength of light that the telescope is sensitive to. If you observe at a shorter wavelength, you can get a higher resolution image, which is really important, and I'll get to that later on in the talk. Okay, so what I think is really cool actually is that we use the Earth itself as part of our instrument. And so as the Earth rotates, each pair of telescopes is at a slightly different location relative to the source on the sky. And so it can actually observe a slightly different region of Fourier space. And so each pair of telescopes can actually observe a curve in Fourier space, which is what you're seeing here. Also, as the Earth rotates, you can see the additional telescopes come in and out of view as well. Okay, so for the 2017 observations of M87 with the EHT, this is the full information that we had. You can see that there's a lot of gaps here. And so we can't just use that simple math equation to apply to our data to get the image, because there's too much information that is missing. And so it becomes a much more challenging problem, because you need to have an algorithm that will make some sort of guess about what goes on in the gaps where we just have missing data. Okay, and so that's what my algorithm does, is it uses machine learning to fill in the gaps. I will also, before I discuss my algorithm, I will discuss a little bit about other algorithms that fill in the gaps in different ways. But before all of that, I'm going to take you on a tour of the actual telescopes, since I know everyone here loves telescopes. So this is a telescope in Spain. Here we have ALMA in Chile. We also use APEX, which is also in Chile. Here is the LMT, which is in Mexico. This is one of my favorite pictures. The submillimeter telescope is in Arizona. And here we have both the JCMT and the SMA that are both on a mountain in Hawaii. And finally, the South Pole telescope as well. One second, I need some water. Okay, so those were all of the telescopes that observed as part of the EHT in 2017. So we had 8 telescopes at 6 geographic locations. One thing that's really important to keep in mind, though, is that in this talk, I'm really focusing on M87 and not Sagittarius. And due to the location of M87 on the sky, the South Pole telescope actually cannot observe it. And so for M87, we actually only had 5 geographic locations. Okay, since 2017, which I guess I haven't explicitly said this, but everything that the EHT has published so far comes from data that was taken in 2017. We did also observe in 2018, 2021, 2022, and 2023, and we are planning to observe again this year. In 2022 and 2023, we also had 3 additional telescopes Kitt Peak, the Greenland Telescope NOEMA, which I'm showing you here. Greenland Telescope can only see M87 and cannot see Sagittarius Star, so now we've kind of evened it out a little bit. We also have significantly increased the bandwidth, which just means that each telescope is observing, let's say 230 gigahertz, but then also like 228 and 232 or something like that. So we can observe several nearby wavelengths, and that effectively fills in Fourier space a little bit more for us. And then also in 2023, we observed at both 1.3 millimeters and also 0.8 millimeters. Not all telescopes can observe at 0.8 millimeters, but we had a pretty reasonable number of them that were able to do so. We also plan to observe again at the shorter wavelength this year. And as I mentioned, observing at a shorter wavelength gives us significantly higher resolution as well. Okay, so in the left here, this plot is the same one that I showed you that was on the right when that Earth was rotating, right? But here they're different colors because I've labeled them according to the different telescopes. On the right, I'm actually showing you the exact same data, but just in a slightly different way. On the left here, this is two-dimensional Fourier space. On the right, I've collapsed the two dimensions into one, and the x-axis just shows you the distance from the center of Fourier space, such that these blue points here correspond to these blue points here. The y-axis of this plot is the amplitude of the complex Fourier component at that location, or the amplitude of the data that we collected. And effectively, the data that you see here is the only information we had, except for also the phase of these data points. And this is what we had to use to make the whole image that you see. Now, for those of us that have spent years looking at what an image of a black hole looks like in the Fourier domain, we looked at this data and we were absolutely thrilled. We knew pretty much right off the bat that this is going to have to be a ring because it had this characteristic ringing feature, which is effectively a Bessel function. It's actually the addition of two Bessel functions, but regardless, effectively a Bessel function for now. And so I'm going to take just a couple minutes to try to build a little bit of intuition for you as to why we looked at this data and why we were so excited about it and how we knew that it had to be a ring. Okay, so these red data points are the same data points that I just showed you. I am going to start with what I consider to be the simplest possible image, because most things in astronomy are spheres, and so most images are a filled disk or a point source, but in this case, a filled disk. And this yellow curve is the Fourier transform on the image on the left, and the red is the data points. So the first question we're going to ask is it possible to match our data with a simple filled disk? Well, I can change the size of this filled disk such that I can approximate the location of this first minimum. But if I do that, I do a really terrible job approximating the location of the second peak and also approximating the location of where we think the second minimum should be. Okay, so the next thing I'm going to do is I'm going to add a hole in the center of our filled disk here. And now, as you can see, by adding a hole, which by the way, you know, the Bessel function of a filled disk, sorry, the Fourier transform of a filled disk is a Bessel function. The Fourier transform of the disk, the negative disk that I've added in the middle is also a Bessel function. So I've literally just subtracted two Bessel functions, and that will give me this new kind of modified Bessel function, but still having that ringing pattern. And now I'm able to approximate the height of this peak and also the location of this minimum here. And if I blur it, I do even a little bit better. Okay. So obviously that was not the way that we actually analyzed the data, but I hope it gave you a little bit of intuition about why we're so certain that it is a ring and not some other shape. I'm comparing here in this plot both the image of Sagittarius Star as well as the image of M87. So M87 is on the left, Sagittarius Star is on the right. I'm showing these images to scale, showing effectively their relative size on the sky. And then the actual physical size of these two black holes is drastically different because Sagittarius Star has a mass of about 4 million solar masses and M87 has a mass of about 6.5 billion solar masses. Sagittarius Star is in the center of our galaxy, 8.3 kiloparsecs away. M87 is 55 million light years away. So all of these different size scales and distances cancel out almost perfectly, such that the image on the plane of the sky looks almost the same size. But I've also included here a comparison of the physical sizes of these two images compared to different things in our solar system. So here, the solar radius, Mercury's orbit, Pluto's orbit, and the location that Voyager 1 was in 2022 when I originally made this plot. And so the point being that even though they look the same size in the sky, they're actually very, very different. And even though they're quite far away, they're not as gigantic as structures that we're used to thinking about in astronomy. They're still, you know, Sagittarius star at least could still fit comfortably inside of our own solar system. And, you know, M87 isn't that much bigger, right, in astronomical scales. Okay. So now we've arrived at the part of the talk where I will actually start talking about this new algorithm. And it is called PRIMO, as mentioned, and it is based on simulations like the one you're seeing here. And the idea here is that we're going to have this algorithm, PRIMO, learn from these simulations, and it's going to use what it learned to fill in the gaps in Fourier space where we don't have enough data. And so first, I'm going to take you on a little tour of the full kind of training set or image space that I've created with these simulations. You can tell that some of them have really thick rings, some of them have really thin rings. I've actually included a lot of simulations here that are actually inconsistent with our expectations for M87. And I've done this on purpose because I didn't want to bake in our theoretical understanding too much. However, what I am baking in is the understanding that this should be a ring. And I hope that I have explained to you or convinced you in my previous couple slides why we are so certain just looking at the raw data that this image does in fact need to be a ring of some kind. The actual algorithm is agnostic to the detailed physics. It really is completely stupid to the physics, but it cares about image morphology. And so I just need to create as many images as possible that have different shapes that are still rings, but different rings. And then my algorithm can learn from that and then can use that to fill in the gaps of Fourier space and generate a higher resolution image. Okay. So for those of you who are maybe not super into the math, I will try to provide two explanations for this algorithm, one that is more math heavy and another one that is less math heavy. So just bear with me here. So for the more math heavy explanation, what we're really doing here is that we're treating each of these images as a vector in a multidimensional space. And we have created this space of images. And then we can use principal component analysis to find a basis for this space. And what principal component analysis does is it creates a set of basis vectors such that the first n basis vectors will contain the maximum possible amount of information about your original basis for any given n. So it creates a basis that is ordered such that the first few components of your basis have most of the information of your basis space. Okay, now for the alternative, not as mathy explanation, what is happening here is that we use a mathematical equation that can learn the patterns in the images and can create new images that are effective building blocks of the images that we have shown you here. And so then the algorithm can use these little building blocks of images and can add them together and subtract them such that we can approximate all of the images in our original training set and also approximate images that are not contained in the original training set. So let's look at what that looks like visually. So the actual reality is in much more dimensions than free. I unfortunately can only draw in 3 dimensions, so just bear with me because I'm going to give you an example in 3 dimensions first. Okay. So the algorithm is called PRIMO, and that stands for Principal Component Interferometric Modeling. Hopefully my Zoom thing here is not blocking that. Okay, and so this is what it looks like when I use PCA or principal component analysis to find these building blocks of images or to find these basis images. So here's the first one, the second one, and the third one. We can use these building blocks to approximate an example image. So here is an example high resolution simulation. I've also included here a different image, but it's the same image that's just been blurred a little bit. And that's a really important aspect actually, because this algorithm is not trying to generate an image that has infinite resolution or has this like theoretical simulated resolution. It's really trying to generate this image here, which has the maximum allowed resolution for the actual instrument. And so given that, when we create a linear combination of our basis vectors, or in other words, add and subtract our building blocks, we can approximate this image. Now, if we use only free, we get an okay approximation, but it's really not great. If we use a larger number, let's say 20, we do a much better job. So now we're able to, for example, reconstruct this feature, this little dark wispy feature here, which matches this feature right there. There is a bright wispy feature over here, which matches this feature right there. The brightest part also matches between the two, and the dimmest part along the ring also matches between the two. Also, the size and width of the ring matches as well. If you were to use even more, let's say 40 building blocks, you do an even better job. Okay, so what is this algorithm actually doing? Why is this machine learning, and should we trust it, or is it just creating something out of thin air here? Well, what the algorithm is actually doing is it's learning the correlations between nearby regions in Fourier space based on the images. And we can actually use just simple math to find analytically what the expected correlation length is between regions of Fourier space. What I mean by that is, if I have this data point right there, can I learn any information about the nearby points based on that one? Or are the nearby points completely uncorrelated with this data point? And so visually, the size of this correlation length looks like this. And so by learning the correlation length and learning the actual correlations between these nearby points, what we've effectively done is filled in a really large amount of the gaps that we have in Fourier space with this algorithm. The other algorithms also fill in the gaps, but they do not do so using these correlations, and they do not do so in a physically motivated way. They make other different assumptions about what they think the image should look like, such as, for example, preferring an image that has a more compact source, or preferring an image that has lower gradients, or in other words, an image that looks more smooth than others. And also some algorithms will try to maximize the entropy in the image. If you don't know what that means, don't worry about it. It's not actually that crucial for the rest of the talk. Okay. So here are some initial PRIMO results where we have applied PRIMO to synthetic data. So here is the original simulated image, and the bottom here, bottom left, I've blurred that image with the same filter that was used for the M87 image that the EHT published. This is a Gaussian filter with 15 microarc second size. And on the bottom right here, I've also blurred that original image, but I'm using a different filter. This is called a Butterworth filter. For those of you that are interested, if you're not interested, you just need to know that I'm blurring it in a slightly different way. The reason that I'm allowed to blur it in a slightly different way is that I am still suppressing information in regions where we don't have data. So I am still suppressing the resolution that we really can't constrain. But I'm doing so in a way that allows me to keep more of the resolution in the regions where we actually have data than the filter that was used for the EHT images. Then we do a synthetic observation simulating what the EHT does on this image here, and then I reconstruct the image based on the simulated data with PRIMO, and this is the image that I get here. So a few things to note. Our image matches what we expect to see be the like best possible image, which is the image blurred with the Butterworth filter. The ring size is correct. The approximate location of the bright spot is correct. We even are able to reconstruct this little wispy feature right there. And also the fact that there's some extended emission over there, we are able to reconstruct as well. And on these smaller panels here on the right, this is what the amplitude of the data and the model looks like. And this is what the phase of the model and the data looks like. And you can see that it's a pretty good fit. Now, if we compare what we're doing with PRIMO to the other imaging algorithms that use these other assumptions that I just mentioned, there are other additional improvements that we see with PRIMO that's not just a simple resolution. So the top two panels of this plot, this comes from one of the EHT papers. Here is a uniform ring and here is a smooth crescent. If we do a synthetic or simulated observation of that and then try to reconstruct it with a general purpose imaging algorithm called EHT imaging, you can see that even though the original ring is completely uniform, we create these bright spots along the ring. These are complete artifacts. They have nothing to do with reality, and they're completely created by the fact that we have these regions where we have missing data, and the fact that we are filling in those regions in a way that is not physically motivated. The assumptions that the algorithm makes tends to create these bright spots. And so given that we know that these bright spots aren't real, that's actually one of the main motivations for why we use such a powerful filter. And effectively, the reason why we blurred the images as much as we did is because we knew that these features we could not trust and they were artifacts of the algorithm. But of course, PRIMO does not actually create those artifacts. Okay, another way in which we analyze our data within the EHT is by fitting geometric shapes directly to the data in Fourier space. And so we know the image kind of looks like a ring or a crescent. And so can we just use a crescent shape to fit to the data? In many cases, the answer is yes. But in this particular image that I'm showing you here, this and this, by the way, are the same image. The color map is just slightly different and they're rotated, but the actual image is the same. When we try to fit this image with a crescent, and again, this is a synthetic observation of the image, this is what we get. So we're completely wrong. And if we want to fit it with a crescent and a Gaussian, we get this image over here, which is a little bit better, but still pretty terrible. However, when we fit it with PRIMO, we are able to reconstruct even this extended feature here in our reconstructed image. And it's important to note here that this image is actually an outlier compared to the training set of images that I use to train the algorithm. So we're able to reconstruct an image even though it's an outlier. And another reason why I personally was so motivated to construct PRIMO is that it's actually really hard to compare one particular realization of turbulence with another, right? It'd be like comparing what the clouds look like today and tomorrow, even if the actual temperature is the same. And so to really illustrate that, I have a bunch of little images here on the right. Almost all of these images come from the same simulation, but they're just different realizations of the turbulence. However, two of the images come from a completely different simulation. So I'm going to give you a couple seconds to try to guess which one it is or which two they are. Okay, I'm going to give you the answer now. If you got this right, please let me know. I have had a few people get one of them right, but I have not, as of right now, had anybody get both of them right. So either tell me at the end or email me or something, because I'll be impressed. Okay. And so not only is this algorithm able to reconstruct images that don't match any particular realization of turbulence, but we're actually also able to reconstruct images that are completely disjoined from our training set. And so in the example that you see here in the larger panels, what we've done is we've used a training set that all had spin equal to 0.9, and this particular image has spin equal to 0.7. And so a very different spin value, but we're still able to reconstruct this image with PRIMO. Okay, so this is the M87 image that the EHT published, which is significantly blurry, and then this is the new PRIMO image. I have had some fun with this. So, you know, when the M87 image originally came out, people were making this meme and it kind of went viral. And so I've updated it. And so now Homer has a skinny donut or a diet donut so that he can be healthy for longer. I've also had some other fun with some other updates that I'll show you shortly. But the other thing I wanted to mention is that this image, as you see here, does actually have a little bit of super resolution. And so the ring width that we see, we do trust, but there's just a little bit of power in regions and for a space where we don't actually have data. And so I did blur this image a little bit more to show you what the image would look like if we really strongly suppress the power in regions where we don't have data. So it's a little bit blurrier, but it is still significantly higher resolution than the original EHT image that we published in 2019. Okay, and so I've also updated some of the front page newspapers from when the original image came out for fun. And this is what they look like with the skiddier donut. Okay, and here are all three images compared to side by side. And I'm also showing you here what the comparison is between the model and the data for the image at the center here. Now, I know that I've been talking for about 49 minutes, and so I am happy to end my talk on this slide so that we can have time for questions. I do have, I think, like 3 more slides if people want, but really it's just kind of driving home the points a little bit more, but the main points I've already gone to. So I'll let you guys decide what you prefer.
That's a big yes.
I was going to say, it looks like people are giving you the thumbs up to keep going for a few minutes. So,
Okay, sounds good. Thank you all for your patience. Okay, so what I was going to show you is a comparison of the uncertainty in the image. So given that we are making a guess about what is going on in the regions where we don't have data, there is an inherent uncertainty in that. And so no matter what algorithm, no matter what technique we use, there will also always be that uncertainty. What's really great about PRIMO is that it uses this technique called Monte Carlo Markov chain, or MCMC. And what that means is that instead of just having one image, we actually have about 10 million images. And we have the full distribution of images as well as a measurement of how close each of those 10 million images is to the data. And so the image that I
Are we frozen in time?
I wonder if she lost power.
Yeah. I think so. Last frame, it's frozen. Wow. Victor, can you text her? Ah. That wind's fierce out there. I can hear it out my window.
Yeah, same here.
There she is back.
Is she coming back?
Hi, Leah. If you can hear us, we lost you for a moment. Now you're muted.
Oh, hold on a second. I need to. Okay, try it now.
Thank you. Yeah, I wasn't able to unmute myself earlier. Yeah, my internet went out. I am now connected through the hotspot on my phone, but we made it work because my electricity went completely out. So sorry about that. Anyway, do you want to just stop and have questions, or do you want me to try again? Because I'm really good with whatever you guys prefer.
I think we're close to you wrapping it. Why don't you just try to pull it off here? Thank you very much.
Okay. Okay. Okay, can you see my slide?
Yes, we can.
Wonderful. Okay, so I don't know exactly when I fell off, but what I was talking about is how PRIMO gives us not just one image, but 10 million images. And the one that I showed you is the one that is the closest to the data, but we have a distribution and we've actually quantified how close each of these 10 million images is. And so here I'm showing you 3 different images that are not as close to the data, or in other words, the error is larger between this model and the data, but it's not crazy, right? So it's larger, but it's not ridiculous. And it just gives you a good idea of kind of the uncertainty in the image. So all of these, the ring size and the ring width are always consistent. So we're very certain about that. The little wispy feature here at the bottom, it is possible to make that brighter or less bright. But again, as I said, right, the one that fits the data the most is the one that I showed you earlier. We can also change a little bit the relative brightness between this spot here and this spot here, where you can see in this image, they're at a more similar brightness level. To contrast the level of uncertainty in PRIMO, I've also included this image from AAAP paper. And here what we did was we had 4 teams of people. I was in team 1, by the way, who did not communicate with each other. And this was how we originally analyzed M87, is we each independently kind of blindly analyzed the data without talking to the other teams. And then this is the different images that each of the teams came up with. And so again, you know, the ring and the fact that it is a ring and the size and width of the ring are fairly consistent with each other, but the details of the image have much higher uncertainty than what we see with PRIMO. And again, that's because of how we are filling in the gaps in Fourier space. And then that brings me to my summary. So PRIMO does not create the artifacts in the images, like that bright spots along the ring that we see in the other ones. We are able to reconstruct a much more complicated source structure than what we can do with these geometric shapes. And PRIMO fills in Fourier space in a physically motivated way, and it's the only algorithm that does so. We're also not limited to comparing specific realizations of turbulence with each other, but we can compare the whole distribution of the turbulence with each other. And finally, we can reconstruct images even if they are not contained in our training set, but are kind of within the really large and broad space of images that we create. And this allows us to compare the simulations to the data in a more quantitative way. Okay, and with that, I'll take questions. Thank you so much for your patience. And again, sorry that my internet was having some issues.
Well, I think it's amazingly resourceful of you to get back up and running again.
Thank you. I tried.
But I just have a quick question. Why did you guys start with M87? I mean, 53 million light, that's very far away. And Sagittarius A star is a whole lot closer, but I gather there were challenges that made M87 an easier target. And why is that?
Yeah, so even though Sag star is much closer, it's also much smaller. And so on the plane of the sky, the size between the two is actually very similar. And I think I actually have a plot of that. I can get back to it really quickly. And so the size difference is really not relevant. Sorry, here. So this is the size, the relative size between the 2 images on the plane of the sky. So Sag star is a little bit bigger than M87. And so in that regard, it might be a little bit easier. However, when we look at Sag star, we're looking through half of the galaxy. And so there's a lot of interstellar scattering that we need to deal with that really does affect our measurement in the radio band. 1.3 millimeters, the scattering is subdominant, and that's another reason why we chose to observe at this wavelength. But it is still an important effect that does affect Sag star, but does not affect M87. The other part of this is that because Sag star is over 1,000 times smaller than M87, the time scale of variability is about 1,000 times faster. What I mean by that is that the same variability exists for both of them. But in, for example, in the movies that I'm showing you, the time, like the physical time between each frame of that movie is different by over a factor of 1,000 between the 2 black holes. And so effectively, within the time scale that it takes for the Earth to rotate, M87 does not change. However, within that same time scale, Sagittarius star does change significantly. And that means that it's much, much harder for us to make our image because we can't just assume that all of the data that we collected over the entire night corresponds to the same image. And so Sagittarius star is significantly more challenging.
While you have this image up, the slide up, could I ask a question, please? I remember when the data was published on M87, and I was trying to relate the angular dimension of this black hole, what you're seeing in your image here, to the light image of an astrophotograph from an amateur telescope, where M87 has an angular diameter, I'm forgetting, but let's say it's 5 arc minutes or something like that. I don't know what it is off the top of my head, and I remember concluding that this was like a few pixels in the center of my image. Is that correct? Can you describe the angular dimensions that you're showing us?
Yeah, so so the size of M87 is equivalent to the size of a donut on the surface of the moon. Just like intuitively, but in actual units, the diameter is about 42 micro arc seconds.
Right. So it is a couple of pixels in the center of our amateur photograph using one.
I mean, I don't know because I would need to know the size of your pixel, but yeah.
Less than that. Less than that. Yes, less than that.
Okay. Yeah.
Micro arc seconds. You're saying micro arc seconds.
Yeah. Yeah.
A single pixel. Less than
Yeah.
that.
So the resolution of 1 micro arc second, I would be shocked if you have a telescope where 1 pixel is 1 micro arc second.
No, I didn't mean to imply that. I'm just saying it would all be contained within one.
Oh,
pixel.
yeah. It would be much smaller than a pixel for sure. Yeah. Yeah.
Wow. That puts it in perspective.
Yeah. It's the highest resolution, angular scale resolution that humanity has ever achieved.
Good point. Wow.
Yeah. The PRIMO image, particularly. Not to, brag or anything.
Wow.
Okay. I have a question just related to that last point. I was trying to understand the resolution of the Event Horizon Telescope based on essentially the diameter of the virtual mirror, which I guess is roughly the size of the Earth, and the wavelength, which you said is 1 or 2 millimeters.
Yes.
Does that give me approximately the best resolution, or does it end up being a lot worse than that for other reasons?
So I would say that is the approximate theoretical resolution. In practice, as I've kind of alluded to, the image of M87 that the EHT published that you see on my slide here does not achieve that maximum resolution. It is blurred with a Gaussian, which means that we are kind of throwing away part of our data because we didn't want to have the public and scientists focus on the fact that there's a bright spot here, a bright spot here, and a bright spot here, because we don't believe that those bright spots are real. And so we blurred it a little bit more than we really needed to, because the algorithms created these artifacts that are not related to reality necessarily. However, the PRIMO resolution is really achieving effectively the maximum resolution of the telescope.
Okay, thanks. One other question on the same topic. I was just wondering, when this data is being processed, they must know the locations of each telescope to within a few millimeters.
Yep.
And so they would have to consider like the tidal deformation of the Earth or continental drift and that sort of, and correct for those sort of things to get the highest quality data.
Yeah, so you could actually use our telescope to measure the continental drift if you wanted to. Like it's something that matters to us. Yeah. Yeah, you're totally right. In some ways, I know that like we've used GPS for this. GPS isn't quite good enough. In some ways we can like use the telescope itself to like measure some of these changes, but yeah, no, you're totally right. We need to know that really precisely, and we do know that very precisely. And in particular, what matters is the projection of the distance between the telescopes relative to the black hole itself.
Okay, thanks a lot. That all made very good sense.
So how can you be sure that something that you see in the image is a feature and not an artifact? I have a feeling that you're going to lead me pretty far into the weeds here, but you seem pretty confident that certain things that you see are artifacts and not features. How do you know that?
Yeah, so a lot of testing on a lot of work is the simple answer if you don't want to go into the weeds, but I will tell you more information than that, right? So the exercise that I took you guys through about, do we need to have a hole in our circle or not, right? Can we fit just a filled disk to the data, or does the data require the disk to have a hole in it? At a certain level, that is one of the ways in which we are so confident that it is in fact a ring, right? So at the most basic level, the fact that this image is a ring and not a filled disk, we are absolutely completely certain about, because even just visually looking at the data, we were already certain about that. The fact that the bottom half is brighter than the top half, we can also visually see data points that would indicate that that needs to be the case. So the things that we are the most certain about are those two things: the fact that there is a ring, there is a brightness depression at the center of the ring, and the ring is brighter on the bottom. Now, the diameter and width of the ring are also determined by the data. However, there is a degeneracy between those two parameters. And that degeneracy is such that you can change the diameter and you can change the width in such a way that the location of that first dip in Fourier space stays the same. If that is the case, right, then if you have an algorithm that tends to prefer thicker widths, you will have a little bit of uncertainty on your diameter, which is exactly what these algorithms do actually, is that they prefer images that are more smooth, which effectively is an image that has a thicker ring as opposed to a thinner ring. So effectively, yes, we know the diameter and we know the width, but there is still an uncertainty in that. I personally am much more certain in the diameter and width of the PRIMO algorithm. And I'm working right now on a follow-up paper that will use a really large data set of simulated observations to directly calibrate that uncertainty in the ring width and the ring diameter. Now, the wispy feature at the bottom, as I said, there is some uncertainty in that. I personally think it's most likely true that there is a wispy feature, but there's an uncertainty in the relative brightness of that feature and the rest of the image. I hope that.
How much risk do you see in sort of seeing what you expect to see?
So
backup complete.
sorry. Oh,
Yeah.
okay. So I think that we were very careful about that risk early on. So I participated in the imaging of M87 with the other algorithms in like 2018, when we first did this. And I am not exaggerating when I say that we just pushed one button on our computer where we already had a script, where that script could image any image, right? It did not assume a ring. It did not assume a black hole. We pressed one button and the ring came out within seconds. We were shocked, to be blunt about it. Like, we were worried that somebody had injected fake data just to test us, right? We were shocked at how easily the image came out of the data. But also, as I said, just looking at the data itself, I could already have told you that it had to be a ring. And so given all of that, I'm really not at all worried that we are kind of tricking ourselves into thinking that this is a ring. I am absolutely confident that this data requires a ring and that that is the unique reasonable solution to the problem of reconstructing an image from that data. I hope
Okay.
that helps you.
Yes, thank you, thank you.
Hey, Leah, this is Mike DeMario. It's a wonderful
Hello.
talk, wonderful
Yeah.
talk. Learn a deal. Thank you. Question on the missing data, though. What's the plan on obtaining the missing data? Is that a function of expanding the radio bands, or is that something else?
It's both. So I mentioned that we have observed since then, and those observations will already help us to fill in those gaps. I do have this slide, but I don't have the slide readily available of like what the baseline coverage looks like for like 2023, for example. I have that. I don't have it to show you right now. But it does look a lot better. We do a much better job with the additional telescopes and the increased bandwidth. We do even better when we add the shorter wavelength. But of course, the images aren't exactly the same at the two wavelengths, so you need to be careful in how you use the data from both wavelengths to make one or multiple images. But yeah, adding more telescopes, observing multiple days so that you can learn more about the variability, observing different wavelengths and increased bandwidth. All of these things are things that we're actively working on and have, large scale proposals in the works or already submitted for that kind of thing.
Right, so that would mean that specialized scopes or radio telescopes per particular band would have to be built and located on the planet sufficiently to be able to obtain the data that you would need.
Yes and no, actually. So all of the telescopes that we're using so far, not a single one was built for the EHT. So they were
Okay.
all telescopes that already existed for other purposes. They do need to have some changes made to them. So we need to add a different receiver that can operate as a VLBI instrument. We need to add the back end, which is the thing that actually collects the data, because it turns out that it's really hard to save data to a hard disk at the speed that we need. So that's actually a really complicated problem, but we've solved it for all the other ones, right? But effectively, we would need to create another one of those systems for additional telescopes. So for example, the free telescopes that have been added to the array, Kit Peak is already an existing telescope, just a new receiver, right? Noema is a brand new interferometer in Europe. It was already being built. It was not built for the EHT, but we were able to kind of join that project at an early enough stage where the interferometer was built such that it can work with us, which is wonderful. The Greenland telescope is, I would argue, the telescope that is the most motivated by the EHT in the sense that it already existed. It's actually a prototype for one of the ALMA dishes. And so the telescope already existed, but I think that a large part of the motivation for why it is being invested into and used in Greenland is for the EHT. But again, we did not build that telescope. We're just motivating continued support of it effectively.
Great, thank you.
Did the EHT use the correlator at ALMA?
So yes and no. So we use ALMA in a phased array mode, which I will be completely honest, I'm not an instrumentation person. And so the dishes are phased together such that they can be such that all of the data from the interferometer can behave as one single dish within the larger VLBI framework. But we don't, use ALMA to like fully make an image, right? So it's correlated, I would say kind of, but it's a little bit more complicated than that. And unfortunately, all of the details I'm not an expert on. But there are people within Princeton that I'm sure would do a better job explaining that than I did, and I apologize.
So I have a data question. So when you show the sparse data, and we see a bunch of clumps of little dots for the different pairs of telescopes. But each of those little clumps look like curves. Is that curvature because the Earth rotating?
Yes, exactly. So that has to do with the fact that as the Earth rotates, the pair of telescopes moves along a curve through space relative to the location of the black hole.
No. Okay, that's right.
Yeah. Sorry, there are also some questions in the chat that I see now. Sorry.
Yeah, go ahead with those.
Okay. So in a direct message to me, Bill asks, at what point is it appropriate to move on to other black holes and analyze the differences and similarities versus fill in the holes in the M87 data? Very, very, very good question, which has a sadly quite disappointing answer. So M87 and Sagittarius Star are really like the perfect black holes for us for a variety of reasons. They have to be really bright at 1.3 millimeters and really close such that we are able to resolve their black hole shadows. M31, for example, is another black hole, or it's a galaxy that contains a black hole that is, not that much smaller than these two, but it's just not bright enough for us to be able to use it. And so effectively, these two are like the best ones by far. We do and have actually published images and papers on additional, more distant black holes, but we do not see the ring for those. We see like the jet, for example. And those are still really interesting results and beautiful images, which I highly recommend you guys look up and look at, because pretty much all of them have a press release accompanying them as well. And so we do that. But it's a different science case because we cannot resolve the black hole shadow for those because they are just too distant, and the ones that are closer are not bright enough. Okay, there is another one is why not use another black hole instead of M87? Again, M87 and Sagittarius Star are the only ones that we have that are bright enough and close enough that we can actually resolve this. But the reason that I use M87 instead of Sagittarius Star is because it's the easiest one to start with. I don't need to worry about variability and I don't need to worry about scattering. I am working on Sagittarius Star, but I have not finalized those results yet. I'm scrolling back up. Somebody asked, what did you learn about gravity with PRIMO? As of right now, I have not published a new test of gravity. However, I've done a new test of gravity with PRIMO. I've done a lot of work within the EHT for tests of gravity. So a lot of the tests of gravity with the EHT papers you'll see, I've been very involved in, including the big Sagittarius Star testing gravity paper that came out in 2022. I co-led that paper with one other person. All of that being said is that the main issue there is the uncertainty on the diameter of the ring. That is what controls how powerful our test of gravity is. And theoretically, we have both a observational or instrumental uncertainty, and we have a theoretical uncertainty. And for the theoretical uncertainty, one of the things that really controls that is that the width of the ring acts as an upper bound on the uncertainty, theoretical uncertainty on the measurement of the black hole shadow. And so the fact that the PRIMO image has a ring width that is smaller by about a factor of 2 is really promising for our ability to publish a new test of gravity with an improved error bound using the PRIMO data. However, I want to be very, very, very careful about that. And so I will only publish that new error bound after I've completed the work that I'm doing right now, which is a complete and really thorough calibration of the algorithm and calibration of the ring width and ring diameter measurement. Okay, I'm gonna keep going backwards here. I think that was it. Okay. Yes, okay. Are there any other questions that I missed?
Is the signal only coming from hydrogen nuclei in the magnetic fields, or is it possible that other nuclei contribute to the signals?
It's actually coming from the electrons. So this is primarily synchrotron radiation of the electrons that are spiraling around the magnetic fields. And as they are accelerated by the magnetic fields, they release radiation.
But there's no signal from nuclei?
No.
From protons?
Not at this wavelength, no.
Right.
They are hot, but at this wavelength, the dominant emission mechanism is not the thermal radiation from the protons, but rather is the synchrotron radiation from the electrons. Which I should also say, it's probably not, I mean, there's still a lot that we don't know, so it's possible that it's H2, but most people in the field think about these things as protons.
Thank you. Victor?
Anyone else?
All right, well, I think if we've exhausted all the questions, thank you very much. We all appreciate the talk. It was very illuminating. Thank you.
Good luck.
Thank you so much
Fascinating.
for your interest and for your attention. I really appreciate it.
Yeah.
Thank you.
Well-
And we do hope we can, have some outreach activities together in the not too distant future.
Yeah, I meant to say earlier, but thank you to everyone that helped me out in my stargazing event. Not mine, but our stargazing event. I really, really appreciate it. I really love doing outreach, especially with like high school and middle school kids. And I love organizing events like this, but I'm completely useless and completely clueless when it comes to actually operating a telescope. I have a telescope and I always delegate its operation to somebody else. So I really, really appreciate and admire your expertise and appreciate that so many of you were able to come out and help us out. We had over 120 people come that day. And we're still getting feedback, even when I just go to lunch during my workday, I'll run into somebody, they'll be like, oh, we really, really enjoyed that. Thank you so much. That was so great. So thank you, thank you, thank you. I super, super appreciate it. I hope that I can count on you for future events like that, because I do like to organize that kind of thing. So
I think that sounds great. I think we would love to cross paths with you in that way again, and also to get you out to our Washington Crossing Observatory sometime if you have not already done so.
Oh, I've never gone. I would love to.
Yeah.
I would really, really enjoy that.
But that'll be another day, not these winter blasts, so.
Yes. Summer is better for the Brazilian for sure.